with compensation, the magnitude of g of j omega is going to be magnitude of 1 plus magnitude of 2 in decibels, right. So, with compensation, consequently the value of the gain crossover frequency would increase, okay. Hence, the phase of 2 would become more negative at the new gain crossover frequency. Right. Thus, what we do is that in order to avoid any conflict, like because the phase margin may decrease below 50 degrees due to this phenomena, thus we would design the lead compensator to provide an additional phase of 5 degrees to 6 degrees to account for this effect. Okay, so that is what we are going to do, okay, because the phase of the second factor is going to become more negative. So, if I still keep the phase contribution of 1 to be 32 degrees, what will happen is that the sum will fall below 50 degrees, right. So, that is what is going to happen. So, what we do not know the new gain crossover frequency yet. So, but as a rule of thumb, what we do is that we typically add 5 to 6 degrees to the number which we have calculated just now. So, instead of 32, we design the lead compensator to provide a phase of around, let us say, 38 degrees, okay. So, that is what we typically do, okay. I hope it is clear what essentially we are doing. Hence, let us design the lead compensator such that it provides a maximum phase, okay, of phi m. You remember what phi m was, right? Phi m was the maximum phase contribution, right, for the lead compensator factor, okay. So, of 38 degrees. Let us say we add 6 degrees to 32 degrees. Let us say we say that the the lead compensator, let it provide a maximum phase of 38 degrees, okay. That is what we are going to design for. So, this implies that phi m is 38. This implies that what was sine of phi m, if you recall from the previous class? It is going to be 1 minus alpha divided by 1 plus alpha, right. So, if you use this, what will happen is that you will get the value of alpha to be 0.238, okay. So, that is what we will have, okay. Is it clear how we got alpha? So, we essentially calculate what was the existing phase margin without compensation. Then we find out what is the additional phase that should be provided to the lead compensator by looking at the required phase margin, and then what we do is that we add a correction term, because the gain crossover frequency is going to be shifted to the right with compensation, alright. So, that is why we just added a correction term, okay, to the required phase of the lead compensator. That is what we have done. Is it clear? Okay. Now, let us go to step 3. Step 3 is to find the value of t. So, in a sense we have found alpha. If we have found alpha, have we found Kc? Yes. So, if alpha is 0.238, immediately you note that K equals Kc alpha. What was K? 10, right. So, this implies that Kc is going to be 10 divided by alpha. So, immediately you will see that value comes to around 42.02. So, what were the three parameters that are involved in the lead compensator? Kc, alpha and T. So, we have found Kc and alpha. What is left behind? Capital T. So, let us find capital T. Okay, that is what we are going to do. So, let us say find capital T. Okay. For this, recall that omega m is going to be equal to 1 divided by square root of alpha times T. Okay. So, this expression I leave it to you as homework. Okay. The magnitude of 1 plus j omega t divided by 1 plus j alpha omega t at omega equals 1 divided by square root of alpha times t, that is going to be equal to 1 by square root of alpha. Okay. So, that is something I leave it to you as homework. Okay. Pretty straightforward, right. So, what is this magnitude I am calculating? I am calculating the magnitude of the sinusoidal transfer function corresponding to Ts plus 1 divided by alpha Ts plus 1. That is what I am doing, right. That is this. Okay. So, this I leave it to you as homework. Okay. Pretty straightforward. You just substitute the the frequency at which you get the maximum phase, right. And please note that this should be our new gain crossover frequency. Why? Because our lead compensator is going to provide the maximum phase at omega equals omega m, and that is what I want as the new gain crossover frequency, would I not? Why? Because that is when my phase margin would be most positive, right. So, we want omega m to be the new gain crossover frequency. Okay. So, what is g of s? It is Ts plus 1 divided by alpha Ts plus 1 times 40 divided by s times s plus 2. Alright. So, this is what we already have. So, consequently, g of j omega is going to be equal to 1 plus j t omega divided by 1 plus j alpha t omega, okay, multiplied by 40 divided by j omega times j omega plus 2. Okay. So, we want omega m to be the new gain crossover frequency. Okay. So, let us say we call this to be omega gn. Okay. Now, at the new gain crossover frequency omega m, the value of 1 over this particular factor is going to be equal to, this value is going to be equal to 1 divided by square root of alpha, which is essentially calculated as 2.05. Okay, right. So, thus this implies that at the new gain crossover frequency, omega gn, the magnitude of 40 divided by j omega gn times j omega gn plus 2 should be what? See, at the frequency omega m, which should be the new gain crossover frequency, the magnitude of the first term is 2.05, right. So, I want to find what should be the magnitude of the second term, so that the product becomes 1. So, what should be the magnitude of the second term? Should be the reciprocal of this term, right. So, this should be 1 divided by 2.05. 0.05. Is it clear? Pretty straightforward. So, you use this to solve omega gn to be 8.9456 radians per second. Okay, please check it out. Okay, so once again this I leave it to us one intermediate homework. Okay, pretty straightforward. We have already done for 2 cases, so please do that. Okay, so that's it. Yeah. So we are just adding a factor of safety, and we are essentially dealing with equalities. Yes. Okay, you are right. It says at least 50 degrees. If you want, you can work with inequalities. So, but what we are doing is that, like, so in order to get specific values, like for design purpose, like we just put some additional buffer, and then we are working with equalities. Okay. Finally, we will come back and check. Okay, that I am going to leave it to you as homework. Okay. So you have to go back and check whether it's satisfying the performance requirements, right? Okay. So we are almost there, right? So now note that we want omega gn, we want omega m. What is omega m? Omega m is the frequency where the lead compensator provides the maximum phase, okay, to be omega gn. And what is omega m? 1 divided by square root of alpha t. So this implies that 1 divided by square root of alpha t should be equal to 8.9456. So from here you can get t. You will get t to be 0.229. Okay? Because alpha you already know, right? Alpha value has already been calculated, right? Was 0.238. So you plug it in, and then like you substitute, and then like you will get the value of capital T to be 0.229. So that's it, we are done, right? So this implies that the controller transfer function is, which is Kc alpha times Ts plus 1 divided by alpha Ts plus 1, that's going to be equal to 10 times 0.229 s plus 1 divided by 0.0545 s plus 1. Okay, so this is the controller transfer function. Okay, so then the open loop transfer function of the compensated closed loop system. Closed loop system, what is that going to be? Is going to be g of s times h of s, which is going to be nothing but c of s times p of s, right? Because h of s is 1. C of s is this 10 times 0.229 s plus 1 divided by 0.0545 s plus 1, and the planned transfer function is 4 divided by s times s plus 2. Okay, this is the open loop transfer function, and this is the controller transfer function. Okay, this is the lead compensator that has been designed. Okay, so as homework, check that the above design satisfies the prescribed performance requirements. Okay, so that is a check which I want you to do. Okay, so you go back and check whether kV is, what did we want kV to be? 20, right? Correct? So you can immediately see that kV is 20, you multiply by s, take limit s tending to 0, kV is 20, right? So check whether gain margin is at least 50 degrees and phase margin is at least 10 decibels. Okay, please do that as homework. Okay, you will see that the design will be specified, right. So, but you can make one more observation, right. Please note that the value of omega gn has increased, which would mean that the bandwidth of the system has increased, right. So, but then what was your observation if the bandwidth increased? So, note that omega gn increased implies the bandwidth has increased with compensation. Okay. But what is the price we need to pay? So, the price was that, if you go back and think about it, but we needed to increase the open loop gain. Okay, open loop, what do I mean by open loop gain is, if you substitute S equals, what to say, you take the steady state value, okay, you take KVE, right. So, you initially we had it as 2 for the plan, right, we had to increase it to 20, right, to essentially ensure that the low frequency components were not attenuated. So, that is something which we discussed yesterday, right, because with a, if you recall, if you go back to yesterday's class, we saw that one limitation with the lead compensator was that the low frequency components were attenuated, right. So, you see that the low frequency components were attenuated. To in fact, what to say, essentially address this, we need to push this curve up. So, that is why we had an extra factor of 10. You remember we had a gain k, like, so which was 10, right. So, we needed to introduce, I would say we needed to introduce a high open loop gain, okay, to ensure that low frequency components were not attenuated. But what is the flip side? So, that is why we calculated k to be 10, if you recall, right, the first step, right. So, this has two effects. One is cost increases when you increase the gain of the system, okay. Second thing is also the high frequency noise gets slightly amplified, right. So, that is something which we need to remember, right. So, I just want to reiterate those 2 points once again, right, through this example. Fine. So, this is an example which essentially shows you the process for designing a lead compensator. We will stop here for this class, and when we come back, what we are going to do is that, like the final theory class, what we are going to learn is about lag compensator and lag lead compensator. Okay, I am just going to tell you what is the purpose and structure of those compensators, and then we will also see, like when to use them, right. Then we will recap the entire course once in the next class. Fine. Thank you.